Hello everyone, thank you for watching this video. So I am Lalin Laudis, a postgraduate student with a specialization in VLSI design in M.Tech University. I am here to present my final year project, a modified SA algorithm for wirelength minimization in VLSI circuits. So throughout this project, I am being guided internally by Mr.Amit Sinha, Assistant Professor, Department of Electronics and Communication Engineering, M.Tech Dr.RR and Dr.S.R Technical University. Apart from this, externally I have been guided by Dr.S.Anand, ME PhD, Assistant Professor, Department of Electronics and Communication Engineering, VV College of Engineering. So before going into depth of this project, let us have a short brief note about what made me to do this project, or in other words, what is the basic motivation behind this project. So as we know that the aim of any VLSI project is circuit minimization. An ultimate goal of every VLSI project aims in minimizing the circuit and its parameters. While minimizing the circuits, several parameters has to be considered. Say for example, a wire length minimization, a dead space minimization, a area minimization, delay minimization. As such, there are several parameters that has to be minimized in order to get a minimized circuit, that is minimum circuit with a not large number of transistors in and the reduced size of the circuit. How to solve these types of problems? How to solve the minimization problems are nothing but algorithms are employed in every electronic design automation tools, that is EDA tools, to solve these types of problem, and every EDA tools has their own algorithms to minimize the parameters in a design processes. And next, to say about what are the types of problems. Generally, these problems can be classified as a single objective optimization problem. A single objective optimization problem is a problem in which the minimization, the problem is concerned with only one objective, that is only one parameter that has to be minimized. In other words, for example, if a minimization problem is concerned with a wire length alone, that is only wire length has to be minimized, then the problem is said to be a single objective optimization problem. Whereas on the other hand, if the same problem is concerned with minimizing wire length, dead space, area and several criteria, that is several objectives has to be minimized, then the problem is said to be a multi-objective optimization problem. Generally, these two problems are said to be NP hard in general, that is the non-deterministic polynomial hard problem, which means that the exact solution of the problem cannot be obtained at any cost. However, a solution very near to the best solution can be obtained by stochastic methods. Stochastic in the sense it is completely randomized, and meta-heuristic techniques are also employed. So how to solve these types of problems? We have seen the problems, we have seen about the different minimization that has to be done in the VLSI circuits. Now how to solve these problems? Researchers have successfully employed genetic algorithms, evolutionary algorithms and several other stochastic methods like particle swarm optimization and colony optimization algorithms to solve these types of problems. Moreover, meta-heuristic techniques namely simulated annealing was also employed for solving these types of minimization problem. However, on comparing this performance of these algorithms, simulated annealing worked very well while comparing the performance of other algorithms. That is, simulated annealing was a very powerful tool to work with the minimization problem concerned with VLSI design. So we have chosen that we are going to do something related to simulated annealing. So before going into depth, let us have a short brief note about what is this simulated annealing, the basics of simulated annealing, just a short slide. The term annealing, it comes from the analogy of mechanics. The basic principle behind the simulate annealing process is that we can see from the picture demonstrated here, that is, in a hot temperature, the atoms are free to move everywhere. But as the temperature steadily cools down, as there is a gradual decrease in temperature, the atoms are restricted to move and hence they form a perfect lattice structure. The basic principle behind the annealing is this. That is, in a hot heat the metal to a very high temperature and gradually makes to cool it so that we will get a perfect crystal. So how would it help in solving a real life problem? Let us assume the same thing, that the atoms are compared with a number of solutions, that is several number of solutions in a such space, where when the iterations goes by, that is when it goes gradually cools down, they are restricted to certain objective functions, they are restricted to some criteria, and hence they form a perfect lattice structure, and in a real world problem it gives a perfect solution set. Generally, simulated annealing algorithm is employed to find the maxima or minima of a problem. Here are some of the parameters on which a simulated annealing algorithm depends upon: the area, the cooling temperature, the acceptance probability, and also the stopping criteria as well. The acceptance probability is a very important parameter of simulated annealing because only the acceptance probability separates the simulated annealing process from other stochastic methods. We will be having a short look about this acceptance probability in the following slides. So, coming about examples of simulated annealing. Traveling salesman problem was one of the world's toughest routing problem, and it is successfully been solved by using simulated annealing algorithm. And also, problems related to VLSI floor planning, that is minimization of dead space, have also been successfully solved by using simulated annealing algorithm. Apart from these problems, other real world problems or optimization problems are also successfully solved by using simulated annealing algorithm. So we are talking about simulated annealing algorithm. Now, how does this algorithm works? Let's have a look at how this algorithm, what is the flow of this algorithm. As every algorithm, simulated annealing algorithm also starts with an initial configuration where it searches for a randomly search for a single just a solution, and next it selects a neighborhood solution, neighborhood point, and the next thing is that evaluate the cost function based on the given objective function. The cost function of the selected point and the neighborhood point is analyzed, and the cost is calculated. Next, if the cost function is better, then the new solution is accepted, but else here comes the beauty of simulated annealing. Even if it is worse than the better solution, is accepted but with a limited probability. This is what the acceptance probability is all about. So if the solution is better, it straight away accepts the solution, but else it is worst, it accepts but only with a limited probability. And finally, the algorithm stops working when the quality is reached. So the entire simulated annealing algorithm can be explained by using this diagram. So we can see that at initial temperature, that is at initial iterations, there is unconditional acceptance. We can see that there is unconditional acceptance. So every solutions can be accepted as a best solution. But as the iteration goes by, as we go down the iterations, as the temperature decreases, there is only the acceptance probability. That is, the solutions are accepted only with a limited acceptance probability. Here it is e power minus lambda c by temperature, which is the probability for annealing process. So at the final iteration, worthy solution, that is the best solution, is obtained. So again we have studied about simulated annealing. So next thing is what we are going to do something different by using this simulated annealing. What is my own contribution? What should I contribute to this project? So before going, let us have a short survey of the papers regarding simulated annealing. So this paper, simulated annealing algorithm, this is the first paper regarding annealing process and simulated annealing in the Science Direct. This was developed by Professor Kirkpatrick and his crewmates and his fellow mates, and this paper elaborates how to implement the process of annealing to solve optimization problems. The next paper is modern floor planning based on B-star tree and fast simulated annealing. What I inferred from this paper is that the simulated annealing algorithm can be modified, and also the representation of the modules, the representation of the blocks in the VLSI floor plan is done by using B-star tree. Next is that the customized simulated annealing algorithm for optimization problems. What I inferred from this paper is that the probability value, the temperature value, and every values in the simulated annealing algorithm can be customized based on the user requirements. In other words, the complete simulated annealing algorithm can be customized based on the requirements of the user. So the next paper is archived essay algorithm. That is, it can be written as AMOSA, which means archived multi-objective optimization by using simulated annealing. So this is a very interesting paper, and it has a very large number of citation in Google Scholar Index. And what I inferred from this paper is that the simulated annealing algorithm can be employed for multi-objective optimization problems as well. And this particular paper, this particular research was carried out by Professor Kalyan Moidev of Indian Statistical Institute, and this particular paper is developed by Kangal Labs, that is Kanpur Genetic Algorithm Laboratory. So when we have a glance over the survey papers, it all shows that the simulated annealing algorithm can be customized, can be modified. It says that the simulated annealing algorithm can be modified. So what we are going to propose, what is our work, what is our contribution to this work is that we propose a new type of annealing process called spheroidizing annealing. So what is this spheroidizing annealing? This process, the spheroidizing annealing, is also mimicked from the analogy of mechanics. Generally, spheroidizing annealing is employed to to obtain a desired physical properties, whereas annealing always converges to the best solution. On the other hand, a spheroidizing annealing converges to the required solution. The highlights of the spheroidizing annealing process are: it minimizes the number of iterations, it maximizes the exploration capability, it searches for an extended period of time. So how does the algorithm goes? What is the run procedure of this algorithm? As usual algorithms, it starts with an initialization phase. It calculates the average uphill cost. It does spheroidizing search. What is this spheroidizing search? This is the thing that makes spheroidizing annealing different from the normal annealing process. So what is this is, in a certain iteration, in a normal annealing process, under a certain iteration, the algorithm search for a global optimal solution. Whereas in a spheroidizing search, the algorithm does search for several local optimal solution, and the average of every local optimal solution is taken as the global optimal solution. This is the major highlight of a spheroidizing annealing, that is a spheroidizing search. And these are all some of the important modules of a spheroidizing annealing, that is a calculation of uphill cost, the objective function declaration, the schooling schedule. The cooling schedule can be done by using this equation, that is Tn equation, where n is the current temperature count, delta average is the average uphill cost, P is the initial probability to accept uphill solutions. The next thing is that when does the algorithm has to be stopped? This has to be declared, right? So here we go. When the required quality is met, that is when the algorithm feels that we have attained the required quality, then the algorithm could be stopped. Sorry. When the rejection rate is greater than the limit of the rejection rate, the algorithm could be stopped. The limit of the rejection rate is nothing but we will be initializing the limit of rejection rate during the initialization phase. So next is that when the temperature goes beyond the initiated temperature value, that is this too we will be initiating in the initialization phase. When the temperature, that is the number of iterations maybe, it goes beyond the initiated value, the algorithm must be stopped. Next, let us have a look about what are all the limitations, what are all the shortcomings of this proposed algorithm. It was found that when 3 consecutive searches does not find out a better solution, the algorithm fails in its operation. The next is that when the temperature of the algorithm approaches very near to 0, the algorithm fails in its operation. However, the lowest value of temperature is 0.0183, and it is found out by researchers, and the algorithm could be designed with the lowest value of temperature 0.0183, so that it gives the very best solutions. And also for very higher temperature, the algorithm does not work well. So we have designed the algorithms and how to test this and the working processes of this proposed algorithm. Sorry. I have employed MCNC benchmark, that is Microelectronics Center for North California. They themselves may have maintained several benchmarks for testing VLSI circuits. So here we go about the details of the benchmarks. So here are the circuit names: APTE, Xerox, HP, AMI33 and AMI49. They have their respective number of modules, number of nets, number of input output pads and number of pins as well. So simulation details, I have used C and C++ programming language to code this algorithm, and also I have simulated this in Microsoft Visual Studio 2010 tool. And the simulated system configuration is that Intel Core 2 Duo processor, 32-bit operating system and Windows 7 operating system, which has a RAM of 3 GB. So when I run this algorithm, I'll be getting an output screenshot like this. That is, it says about the authors of the project paper, and also it asks for the benchmark that has to be taken into account. So when we give the benchmark, how to give the benchmark is that we will be mentioning the file name .exe. With a space, we will be giving the benchmark. For example, I have given the benchmark as HP. So this problem, this algorithm now takes into account of HP problem and just simulates it. So we have run the problem. So it's time to analyze the results of our project in various dimensions. There are several dimensions in which the results of this algorithm can be analyzed. Let's see one by one. First, I've considered the problem as a multi-objective optimization problem where several criteria has been taken into account. Say for example, wire length, dead space, area are taken into account for minimization. So when I simulated while considering this as a multi-objective optimization problem, I got the results as tabulated. The fast essay, that is, I have mentioned it as star. This results I have taken from the literature. While drawing a graph plot, we can see that here the cursor moves. The SSAA is always more than the fast essay, which means that it maximizes the problem and it does not minimizes any parameter. So this is the result while we consider this problem as a multi-objective optimization problem. The next thing is that we are giving equal importance for alpha and beta. What is this alpha and beta? They are nothing but wire length and the dead space of the VLSI floor plan. So while considering this as given as equal importance, I got the results as tabulated. In a similar way, the fast essay results I have taken from the literature. While drawing the graph, even this too does not minimizes anything, but it whereas on the other hand it maximizes every problem to a very certain level. The next is that while considering this problem as a single objective optimization problem, that is only wire length alone is taken into account. So as usual, the fast essay value I have taken from the literature. While drawing the graph plot, we could find that the periodizing simulated annealing algorithm has been minimized for every respective problems, and there is a considerable amount of minimization has been take place in every problems. So this is a comparison chart between SOOP, MOOP, and while giving equal importance. So in every cases we can see that while considering the problem as a single objective optimization problem, there is a minimization has been take place, whereas while in the other cases there is no minimization. So on observing the analysis part, we would have concluded that our results are out, right? So here we go about the results. Our algorithm works very well for the single objective optimization problem, and the final results are as this. This is the graph plot for our final results. So we can see that for every problem, APT, Xerox, HP, AMI33, and for AMI44 as well, there is a considerable amount of minimization has been taken place for every circuits. But so we have concluded our project, but research is a long way travel, isn't it? Yes, of course. So the future scopes, the future direction of research has to be explained and elaborated in this project itself. The first thing is that a multi-objective approach in the design can be employed. That is, for this project, we have considered the problem as a single objective optimization problem. Whereas from the literature survey, we came to know that there was a algorithm, that is AMOSA algorithm, which could be employed the simulated annealing for multi-objective optimization. In a similar way, for spheroidizing simulated annealing also, the multi-objective optimization problem could be employed. The next possible direction is that employing these algorithms for parameter fluctuations as well. That is, in VLSI circuit, as I said, that there are number of parameters has to be minimized, and one of them is a parameter fluctuations, that is the scaling parameters and so something like that. So this algorithm could be employed for minimizing the parameter fluctuations in VLSI circuits. The next possible area of research is that the crossover of B star tree representation. That is, for representing the blocks in the VLSI floor plan, we have employed a B star tree representation. But while in every stochastic method, there must be a crossover operation that has to be taken plot. But this part, that is crossing over of two B star trees, the research in this area has not taken place in anywhere. So this is a very possible area of research where two B star trees could be crossed over. So in order to prepare for this project and prepare for this paper, I have referred several papers, research papers. So let's have a glance over that. So these are some of the papers which I referred to prepare this project. So next is the contribution of my entire M.Tech program. Thus, apart from this final year project, what I had done in the past 2 years is the next we are going to have a short look. So, what are my past works there? Completed works are there. First one is this modified SA algorithm for wirelength minimization in VLSI circuit. This is my project paper itself, and it is published in IEEE International Conference on Circuit Power and Computing Technology. Next is that FPGA implementation of smart card based license management using iris scanning approach. This I did with a social concern, and this too is published in IEEE International Conference on Science, Engineering and Management Research. The next is that a study of B star tree in VLSI floor planning. In this paper I studied about the representation of B star trees, the operation of B star trees, and how it could be employed for VLSI floor planning. I studied about this paper, and it is a study paper. Next is that a study of various multi-objective techniques in simulated annealing. So in this paper I have studied about how the simulated annealing could be employed for multi-objective optimization problem, and what are all the modules in the multi-objective optimization technique by using simulated annealing. This paper, Metaheuristic Approach for VLSI 3D Floor Planning, it gives an advanced view of this floor planning. That is, till now we are minimizing the floor planning based on a 2D function. But while in the Metaheuristic Approach for VLSI floor planning, it employs simulated annealing for a 3D floor planning as well. So here are some of my current works that I am working on right now. So this is a land domination based evolutionary heuristics for VLSI floor planning. This is a purely evolutionary algorithm, a bio-inspired evolutionary algorithm, which is completely based on some of the behaviors of lion, and it could overcome the past research works. This paper is under preparation. And next is that Aadhaar license management system in India by Aadhaar IDs. There is a novel license management system which employs the Aadhaar IDs, which is the unique identification number, and this paper has been communicated for review. And the final is a study various NP hot problems in VLSI and the need for biologically inspired heuristics. This problem addresses what are all the various problems in VLSI and what is the need of a biologically inspired heuristics in solving this problem. Why the need for the biologically inspired algorithms is more necessary to solve complex problem related to VLSI. This paper is also under preparation. So thank you for listening my presentation, and any questions? Well then, if you do like my presentation, my inbox is always open for your valuable comments, feedbacks and queries. So my mail ID is lalin.vlsi13@welltechuniv.edu.in. I repeat, lalin.vlsi13@welltechuniv.edu.in. So if you do like to watch this video again, it is available online at www.youtube.com/user/LALINLAUDIS1/videos. I repeat, www.youtube.com/user/LALINLAUDIS/videos. Finally, thanks for